Good morning, everybody. I hope you guys are doing well today and enjoying the nice weather for once. I believe it's above 40 degrees. Hey, it's 50. It reached the 50-degree mark here, so yay. Almost 70. Wow. See, that's one bummer of living on the lake is it's always like 5 to 10 degrees cooler sometimes, so I think we did Isaiah's, yeah. All right, just a couple of announcements. Yeah, I think it's only supposed to be in like the low 60s by me too, if we're even lucky. Chance of rain today, so we'll see. Fingers crossed I can get outside at some point today and enjoy the sunshine. All right, as far as announcements go, I don't really have too much that is new. Prom tickets are on sale now, so if you have any questions regarding prom, send them my way. I've been getting lots of them and fielding questions for that. So if you do have any questions regarding prom, just make sure you send them to me, and I can help you with that. We are less than a month away until that final deadline of when work can be turned in. So May 20th is that final deadline for any assignments or tests that are not the final exam. So less than a month away for that. Tomorrow, we will be 1 month away from the last day of the school year, basically. So that last day to turn your final exams in. So crazy to think that we're beyond or reaching that 1 month mark until the last day of finals. No way, you're 18 today. Happy birthday. That means he can get a haircut without his mom's permission. So he can take a picture and send it to me to put in the senior slideshow. See what I did there? Told you I'm not going to let up. All right. Oh, there now he's typing. Must be a lag today. Nothing. All right. So the plan today is to take a look at that 9.05 lesson. It is on mathematical induction. Mathematical induction is another way to look at proofs. So it's been a while since we've seen proofs, probably back in our geometry days, but we did see some trig stuff though. So when we were looking at those trig identities, we did some trig proofs. The good news is we're not dealing with trig so much anymore. So we will be looking at more algebraic type proofs today with our mathematical induction. Mathematical induction is a different process than we're kind of used to with our proofs though. So it's a 3-step process that we're going to be taking a look at today. That third step is going to be the most lengthy of them all. But we'll manage through, and as long as we can stay nice and organized and detailed with our steps, everything should go just fine. Right? And here we thought proofs were going to stay back in geometry. Nope, they follow us through. Before we take a look at this mathematical induction lesson, which is the last lesson of Unit 9, I believe. So after this, we'll be preparing for that Unit 9 test. Thursday's class, I'm actually going to jump forward and we're going to start Unit 10, which is the last unit of the school year. So in Thursday's class, we're actually going to take a look at 10.01 lesson. And the reason for that, I just wanted to double check my calendar there. Next Tuesday, I will not be in my office in the morning. So I'm out of my office from 9 to 12 next week, Tuesday. So because of that, we are just going to start that Unit 10 this week versus next week. So next week we will not have a live class. You guys can sleep in for the morning next week Tuesday, but then we'll meet again next week Thursday. So we'll have class this week Thursday and then next week Thursday, and we won't need to do any recordings in the meantime, because with that pacing there, we should be able to get everything covered still in those live classes. I'll remind you of that no class next week Tuesday in Thursday's class as well. So we're still a week away from that, so we won't keep that in the forefront right now. Okay, any last minute questions here before we take a look at our mathematical induction? Oh no. All right, so as I had mentioned, our mathematical induction is 3 steps. And it looks like there's just 2 steps there, but step 2 is actually going to be split into 2 different pieces. So the first step is showing that it's true for the anchor. And the anchor means when you substitute 1 in for n, do you get the first term of that series or sequence that you have on the left-hand side? So I'm going to go through the 3 steps here in this first example here. So to show that the anchor is true, you're going to let n equal 1. You're going to substitute that into the right-hand side. So 1 squared. 1 squared is equal to 1. 1 is the first term of that series, so that comes out to be true. Usually I'll put like little check marks, but you can put like true after that if you want. If that were to be false, so if we get false after step 1, the anchor is not true, you cannot proceed with your mathematical induction. All right, so if you get a false statement there, you cannot proceed with your mathematical induction. It would not work. Okay, now fingers crossed, most of the time it will, but there is that chance that when you substitute that value in for n, you're going to get a false statement that will not be the first number of your series. And if that happens, you have to stop and say we cannot go any further with mathematical induction. This cannot be proved using mathematical induction. I think you may run into one example of that on the homework. So heads up, I think there's one example that's going to come out to be false on your homework assignment. I won't tell you which one, but I think there is one. All right, now that we've shown the anchor is true, we're going to go ahead and assume it's true for every term k. So that's what this second step means. That's your inductive step. Assume it's true for k. So what that means is basically you're going to take your statement from up above, and you're just going to replace the n with a k. So nothing too dramatic here. We're just replacing that n with the letter k. So we are assuming that statement is now true. If we assume that is true, in step 3, we can prove that it's true for k plus 1. So I'm going to go ahead and change colors here. And what that means is we're going to go ahead and kind of copy the left-hand side there. Now, the only part I'm going to copy is up to this piece right here, because technically all of this is going to drop out when we get to the k squared piece. So when we look at step 3 here, the only thing we really need is taking that 2k plus 1 plus, and this is kind of the tricky piece. Now we're going to replace the k with a k plus 1 equals, And we're going to go ahead and replace that k with the k plus 1 as well. Okay, so it seems a little bit weird, but notice that when we try to prove it true for k plus 1, we still have everything out in front here, although that kind of will drop out because we can replace that with this 2k plus 1 piece, plus our 2 times k plus 1 plus 1. So we need the next term after this, and that's going to equal your k plus 1 squared on the other side. Step 3 is the hardest piece to kind of get used to, but once we do 2 or 3 proofs, it really sinks in and it's not going to be too difficult after that. But the first couple examples are a little bit confusing on what we're supposed to put on each side. So I'm just going to stop talking for a moment, kind of let that sink in. If you're writing notes, you can get that down. Because after we get this statement written here, the only thing left to do is simplify to show that both sides are going to equal the exact same thing. So that's the only step that's kind of left in this process. Oopsie daisy. And you know what? I accidentally made a slight mistake here. We don't want that 2k plus 1. Yikes. Because we're going to have all of this written plus the next term. So here's the next term after this is all written. But all of this is going to be equal to a k squared. So I actually want a k squared out in the front here. So my bad. I knew that this was going to be replaced somewhere. So technically I would have all of this written plus the next term. So this is the next term, that k plus 1 piece. But I can replace all of that with before it. So everything that comes before it, I can replace that with just the k squared because we knew that that's what it equaled from step 2. So that's what we want to start. My bad. I was like, that doesn't look right at first. Now this looks a lot better. All right, let's go ahead and simplify and see if we get the exact same thing on both sides. So the first thing I'm going to do is I'm just going to simplify the left-hand side all the way as far as I can, and then I'll simplify the right-hand side all the way as far as I can. And then hopefully, once I'm done simplifying both of those sides, they will equal each other. Okay, so to simplify the left-hand side, I'm going to distribute the 2 that's inside the parentheses. I'll go ahead and combine the like terms there. And not much else to do on that side, right? So I'm going to go ahead then on the right-hand side, and k plus 1 squared, that's the same thing as k plus 1 times k plus 1. So when I go to simplify that, we're actually going to be distributing. So that is going to be a k squared plus 2k. I'm just trying to see where I made a mistake because we're supposed to get the same thing here. Oh, I know where I made the mistake. Okay, hold on. Does anybody see my mistake that I have? You'll get added bonus if you can find my mistake on the left-hand side. I see it, but does anybody else see where the mistake is? That extra plus 1 is not actually a plus 1. What should it be there? Yep, it should be a minus because of right here, right? All I did was technically replace this n with the k plus 1, and my mistake, I put a plus 1 instead of a minus 1 there. So that is just going to change things slightly. basically it's just going to make that a -1 at the end, which would change that to a +1 at the very end. And then they come out okay. So I noticed that when I went to go simplify those, that they didn't come out to be the same. My constants were different at the very end, which means I probably had a mistake somewhere. So that was then my signal to go back and take a look at the steps that I did on that left-hand side to see if I could find my mistake. And we did. We noticed that instead of a -1, I accidentally put a +1 there. But when we change that and rework the simplification, then it comes out. Okay, so this is now done. We have proven that it is true for our k plus 1. So technically you can do your 3 little triangle marks there and do your QED at the end. So that means that your proof is now finished. It does work. Okay, kind of a little bit of a rocky start for me there, but we'll get better, I promise. Questions with that mathematical induction process at all? So those 3 steps that we're taking a look at here. Okay, obviously we need more than one example to really have this sink in. So the next example here says prove that that is true for all positive integers n. So the first thing we have to do is show it is true for the anchor, which is n equaling 1. So to show that it's true for the anchor, we're going to substitute that into the right-hand side of the problem. And we're going to then simplify to make sure that we get the first term in that series on the left-hand side. And I need to replace the n with a 1. All right, let's see. What do we get when we simplify here? A 1? Yep, looks like it's going to be a 1. Is that first step true? So does that give us the first term of that series on the left-hand side? Yeah, because 1 squared is 1. Yep, so that does come out to be true. All right, so since step 1 worked, we're going to go ahead and move on to step 2. Step 2 is you're going to assume it's true for k. So I'm going to go ahead and kind of replace everything that I see an n here with a k. So we're just rewriting everything with a k instead of an n. Okay, I'm just going to look for typos here because I want to make sure this one goes a little bit better than the last one. So far, so good, though. I don't see any typos or plus signs that got changed to minuses or vice versa. So things look good there. Step 3, and again, the most challenging step, is going to be showing it's true for k plus 1. Okay, I'm going to put in an extra step here at the start of step 3 here. So to show it's true for k plus 1, we're going to take everything that we have, dot, 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 plus k squared plus, so this was everything that we originally had. That was your k squared. Now we need to go one more term out. K plus 1 squared. All right, any questions with the left-hand side before I rewrite the right-hand side? So I'm going to pause there. Any questions with that statement on the left-hand side so far? So all I did was take everything we have listed, and then I added the next term and after that. So that k plus 1 squared piece. On the right-hand side, we're going to go ahead and replace every k with a k plus 1. Whew. All right, and that's what we're sitting at right now. So I'm going to pause again for a moment there. Any questions with how we got that full piece there for that first step? Okay, now we can't simplify what's on the left-hand side yet because we've got to go in and replace all of that plus dot 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 stuff with something more concrete. And we can replace all of that work with what we have in step 2, right? So all of this is going to be substituted with this right here. So I'm going to do that as my first step. So k times k plus 1 times 2k plus 1 all over 6 plus the k plus 1 squared. Okay, so this is what we want to try to simplify now. So we've got to somehow show that those two sides are going to equal the exact same thing. All right, let the good times roll. Let's go ahead and see if we can start to simplify what's on the left-hand side here. So does anybody want to start with the numerator and start multiplying this stuff together? How about you guys start there, and then I'm going to work on simplifying some of the right-hand stuff in the meantime. So let's have you guys multiply these things together, and let me know what you get in that yellow highlighted portion there. All right, Tommy got a 2k cubed plus 3k squared plus k. Isaiah's got the same. Good. All right, the next thing I want you to do is multiply this stuff. So I would probably expand the k plus 1 squared first and then distribute the 6. So let me know what you get when you multiply all of that together. A 6k squared plus 12k plus 6. I'll wait for somebody to second that. I'm sure Isaiah is, or Rachel or Rebecca might be doing that. You guys get the same thing? Isaiah's got the same thing? Okay. The right-hand side, I am just working on multiplying these things together. So what I did here is I multiplied the k plus 1 times k plus 2. And I got this k squared plus 3k plus 2. And I'm going to multiply that now by the 2k plus 3. Notice that both of these have a denominator of 6. So everything is over 6 now. Because everything is over 6, I can multiply everything by 6 to cancel that out. So technically these denominators drop out of the equation now because they all have the same thing. So if everything has a denominator of 6, we can just take it out. Because technically that will be canceled as we multiply everything by 6. So all we're really left with now is what we have in these numerator portions. So how about you guys go ahead, combine the like terms on the left-hand side, and I'm going to work on multiplying on the right-hand side here. So I'll multiply on the right-hand side, you guys combine like terms on the left, and let me know what you get. Get a second. Rachel and Tommy is awesome. Good news. I got the exact same thing when I multiplied those polynomials on the right hand side. So that is going to be the end of step 3. We are now done and we can say QED. This proof is finished. That is in fact a true statement at the very beginning. So all of this will equal what we have on the right hand side. So you can see that that third step takes some time. I think the most complicated piece is making sure you have everything set up correctly at this step right here. And then just making sure that as you're going through that simplification process on both sides, you're not making a mistake there. So with your mathematical induction during step 3, there's lots of room to make an error. So we just want to keep a close eye on our details there and making sure that our simplification is going smoothly. Questions with that process at all? All right. Now, let's take a look at one that looks a little bit more generic. Some of these are going to make us think about all of the algebraic concepts and theorems and formulas that we've learned in the past. So some of these can get a little bit more complex with that thinking out there. So let's go ahead and take a look at example 3. The good news is once we see an example done like it, it kind of sticks on our head and we know to keep an eye out for it in the future. So generally, once we do one together, it isn't going to be too much of a problem if it were to come up again in the future. So that's the good news here. It says prove that 4n minus 1 is evenly divisible by 3 for all positive integers n. So if we need to prove this using mathematical induction, we've got to show in step 1 that that is true for n equaling 1. All right. 4 to the first power minus 1 equals 3. Is 3 divisible by 3? It is. So that first statement works out. So step 1 is good. When we substitute n equaling 1 in and simplify, it is divisible by 3. So that does work out. So step 2 is assuming that it works for k. Okay, I changed to typing because that writing it out was way slow. So assuming it's true for k, that means 4 to the k power minus 1 is divisible by 3. Step 3 is showing that it is true for k plus 1. Okay, so show that 4k plus 1 minus 1 is divisible by 3. All right, so what can we do to see or try to make sure that 4k plus 1 minus 1 is divisible by 3? Any ideas on what we can maybe do there? That exponent really catches my eye. So if we can maybe try to do something with that exponent, that might be a good starting point. Any ideas how I can maybe split that exponent apart? Kind of. We actually don't need a logarithm, but we are thinking about those rules that we maybe learned with our exponents. And I think the logarithm rules had something similar in them. What if we do something like 4 to the k and 4 to the first? If I separate those so we keep the same base of 4, what operation would go between the 4 to the k power and 4 to the first power? A multiplication. Yep. Good. All right. Now, it would be awesome if I could factor out a 4. So I'm going to try to do that, but I can't factor out a 4 from that minus 1. So keep an eye here with me. If I factor out the 4, that would give me a 4k, because technically here's that 4 that we took out from that first term. So that would leave me with a 4k. I have a minus 1, but I want to keep this balanced. So if I want to keep this balanced, what would I have to maybe either add or subtract on the outside to get back to the statement right above it? So think about distributing. So if I distributed this, I would have a minus 4 at the end. But I don't want a minus 4 at the end. I want a minus 1 at the end. So what do I need to add to keep that balanced? I have to add a 3. So I have to add a 3 on the outside if I'm going to keep this equation balanced. Because now, if I were to simplify that, I would get what I have right above it. And wouldn't you know that by adding that 3 at the end, what does that tell me? So if I have 4k minus 1, that's divisible by 3, right? So 4k minus 1 is divisible by 3. If I multiply that by 4, would this product still be divisible by 3? So if this part is divisible by 3 from step 2, if I multiply that by 4, is that product still divisible by 3? It is, right? Because as long as that part in parentheses is divisible, multiplying it by a scalar wouldn't change that fact. It would still be divisible by 3, because 4 times 3 is still divisible by 3. And if I add 3 at the end, would that term still be divisible by 3? Yes. So technically right here, we would call it good because this is divisible by 3. Okay, because 4 to the k minus 1 is divisible by 3. Multiplying by a scalar would still be divisible by 3. And adding 3 at the end would still make that term divisible by 3. Good. And you can check that out if you'd want to. If you want to say like 4k minus 1, if you pick some term that's divisible by 3, like 6, so if you assume this whole highlighted piece is going to substitute to a 6, you could do 6 times 4 is 24. 24 plus 3 is 27. 27 divided by 3 is 9, so it does come out nicely. So you could try to verify that by using some divisible number here to test that out. Divisible by 3 number here to test that out. Okay. I think the hardest part was going from this piece down to here, and then knowing that you had to try to factor out that 4 as well. So those kind of steps are hard to see with this simplification process there. Okay. Questions with that at all? So that was more on the tricky side. We won't see too many things like this, but that one again was you had to think way more logically on how to proceed on these steps in part 3 there. Okay, just in case you need it, we actually saw this in our example 2 here today already, but these are the rules that you would use to find your powers of integers. So if you're finding the power of the first 7 integers of k to the 4th, you can use this formula right here and just let that n be the number of terms that you're looking for. Right, so an example there would be the first 7 terms, 1 to 7. Then they're just replacing n with 7 in that formula. So these are just some shortcuts to help you find summations of some term to a certain power. So we have up to n to the 5th, it looks like, given here, on how we can find the sums of those quite quickly using the formulas on the right-hand side. We actually did already see the mathematical induction for that n squared. So we saw that that does in fact work out. Below you can see that quick example. They want you to find the value of the first 7 terms, because 1 to 7, of k to the 4th power. So using that sum of powers of integers formula here, k to the 4th would be this formula here. They're looking for the first 7 terms, so n would be 7. And then they're simplifying that process here. So when they simplify, they get the sum of 4,676. So I'm not sure if that will be necessarily needed for the homework assignment, but it is just kind of a shortcut route if they do ask about any sums of powers of integers at all. You can use those equations on the right-hand side as kind of your shortcut there. All right, back to our proofs. Woohoo! Use mathematical induction to prove that the statement holds for all positive integers. This might be the last one we squeeze in here today. So step 1, show it's true for the anchor. So show true for n equaling 1. All right, so you're going to go ahead, start on that right-hand side and substitute a 1 in. What do we get when we simplify 1 squared plus 1? 2, is that a true statement? Is 2 the first value on the left-hand side? Yep, good. So we can go ahead and proceed forward. Step 2, assume it's true for k. So that would just be your 2 plus 4 plus 6. And now basically just replacing everything with a k. Okay, step 3, show it's true for k plus 1. All right, so I have all the way up to that 2k, and now I've got to replace the k with my 2 plus 1, or k plus 1, sorry. I was reading the 2 that was out in front of that there. On the right-hand side, you're just replacing every single k with the k plus 1. Okay, any questions with how we set that first statement up in step 3 there? So kind of taking what we had in step 2 and adding on the next term for k plus 1 on that left-hand side, and then replacing all the k's with k plus 1 on the right-hand side. Okay, what can I substitute in for the highlighted portion in that first statement? Because we're not able to simplify with all those little plus and dots in there. We don't even have to go quite that far. Look back in step 2, and what did all of that highlighted portion equal back in step 2? Yep, so that's what we're going to replace it with down below. Okay, any questions with that at all? Let's go ahead and simplify. Let's just start with the left-hand side, and then we will come back and worry about the right-hand side in just a moment. What is this left-hand side going to simplify to? Good. Okay. Always good to make sure I'm not making a mistake here. All right, let's work on simplifying the right-hand side. So I'm going to multiply that k plus 1 squared. Remember, that is a k squared plus 2k plus 1. And then we're going to add in the k plus 1 for that second term there. let's go ahead and simplify and combine like terms. What do we get here when we do that? Yeah, we better get the same thing as before, right? So we can actually get it a step earlier, but because we needed an extra step on the other side, we'll just repeat the same thing twice on that right-hand side. Very good. Once we get the same thing on both sides, we can finish and say that we are done with our proof, and the original statement is in fact true. Okay. Questions with the steps for mathematical induction? So it can be a little bit tricky at times, but just remember those 3 steps. And don't forget that at step 1, sometimes that may come out false, right? So if it does come out false, you just stop there and you say that it cannot be proved with mathematical induction. Okay. And again, I think there was one example on your homework assignment where that does happen, where it will turn out to be false instead of true. So just keep an eye out for that. Okay, any questions with 9.05 at all? Okay, I'll open this up in case I went too fast through any of the examples and you want to go back and copy those down. You can do so now. Kind of, yeah. All right, I'll let you guys go. Have a great rest of your Tuesday. Try that 9.05 lesson before Thursday's class. I'll start Thursday's class off by taking any questions you have from that homework assignment. We are going to venture a little bit forward on the calendar than what will be paced at on Thursday's class. We're actually going to start Unit 10 to kind of get ahead a little bit. Just kind of be prepared for that as well. All right, that's all I got. Have a great rest of your Tuesday, and I'll see you Thursday morning again. Bye, everyone.